Okay, this is AGEC Module 2, Lecture 2. We continue talking about optimization. And think about the problem we saw in Lecture 1. An agent who can write down a profit function and choose the price that will make profits as large as possible. And we call that a specific type. That's unconstrained optimization. So if you can write the function down as one equation and not have to deal with the idea that there are some limits on the choice set, then we call that unconstrained, and that's a place to apply sort of basic calculus and get the solution. So while we use that in analysis a lot, certainly in economics more broadly and in business decision making, and even just sort of standard analysis for demand, for consumption choices, the utility maximization, cost minimization, all kinds of problems in economics, we need the constraint. We need to think about how do they deal with the idea that not all choices are feasible. Okay, more complex decision environments are really a feature, and obviously the more applied you get, the more we get into a class like this where we're thinking about sort of modeling real problems. We're gonna, there's gonna be some abstraction. We are going to have to make some compromises to reality to get these things into mathematical settings, but certainly the more complex ones will have more constraints. It becomes the feature. So typically we'll think about multiple choice variables that can be moved, and they may impact one another as they're adjusted, and then constraints or limits on the choice set. And if we were going to think about these as the sort of core concepts, the first would be feasibility, right? So this is a word that'll come up and potentially in your reading. It's basically the choices that can actually be executed. They are available, right? So some choices may be great, but they're just not feasible. The budget won't allow it. Current technology won't permit us to produce more of X, more of Y, and more of Z because we don't have the resources, or there's not enough. We haven't figured out how to do that. And then there's a second concept called efficiency, and that's basically efficient judgments on efficiency require some criterion. Okay, so we look at all the feasible choices, and typically we can reduce the set of feasible choices, everything that's available to us, down to some that meet a more strict criteria, that says these are better than some others based on this criteria. Okay, so optimality is sort of the ultimate efficiency criterion, right? Can we say someone is making the best choices, giving the economic environment and giving their feasibility constraints, right? And that gives us an answer, or an efficiency sort of criterion that says the best use of resources or the generation of the most returns. But efficiency doesn't always have to be optimality. It can be applied in several different contexts and several different layers, and we'll talk about that a little bit. Okay, but in terms of a sort of broader economic efficiency or allocative efficiency, we can think about optimal resource allocation and our first sort of conceptual constrained optimization problem that we're going to talk all the way through. What if GDP was our goal, and food output and non-food output were the categories that we could use to describe every possible output? Okay, now obviously there are more things than that can be made, but this is a pretty general problem. You could put in 1 million goods, and the sort of basic results we're going to talk about here hold up. So if we were going to produce, the highest sort of national income as measured by GDP, and the two choices are food outputs and non-food outputs, and those have to be made from something, and we have some sort of national resource input or some kind of national allocation of inputs or resources that can be used to be converted into those consumables of food and non-food. And then there'd be some kind of national production function that actually describe that conversion process. So you have this X, the resource base, and then the two potential outputs, and so that's some kind of math function. And so typically what we would do is write down this, well, we call it a Lagrange function or a constrained optimization problem, just similar to the algebraic work you did in Module 1. We're going to say maximize, and then we're going to say it's GDP is the thing that needs to be maximized. And these are supposed to be subscripts. I'm not sure why they went away, but this is R sub F, Q sub F, R sub N, and Q sub N. Sorry about that. I didn't realize they'd gone away. So this is the price of food here, these first two letters, times the quantity of food, plus the price of non-food times the quantity of non-food. That's our measure of income here. And then the constraint just says that it has to fit on this frontier, this transition frontier that converts resources into two potential outputs. So don't worry too much about the look of that constraint. We're going to get away from this mathematical setup pretty quick and get into a graphical setting. This is the Lagrangian function. So if you've had some multivariable calculus with constraints, you've seen this. You can rewrite this where you put the objective part, the GDP part here, and then you put in what they call a Lagrangian variable in front of the constraint. You solve it with some basic calculus tools that aren't too difficult. If we had an extra 6 weeks, we might work on those and think about what they do. But we're an implementation computational class, so we're going to move ahead. But we can learn a lot and get the same exact solution by taking the graphical approach. Okay, and so rather than trying to write that Lagrange thing down, let's just think about that function that describes the transition of input or resources into the two outputs. And let's just plot the non-food output on this axis, the food output on this axis, and just recognize that the level of this curve, this trade-off curve that says you can have this amount of QN and QF, or you can trade it for this amount, or this amount, or this amount, right? This is a trade-off curve. Well, this level of this curve is set by X. One of the factors that tells us what this looks like is how much national resources you have. And you probably recognize this. It's called the production possibilities frontier. It's the set of all possible production plans between food and non-food that are available to this economy. So technically, I guess you could say that we could say you could reserve resources by producing inside of the frontier, but we typically refer to the frontier as efficient because whatever is in X has no value to us. We're talking about economic inputs here. So reserving them makes no sense, so we typically think about the frontier being sort of the full set of efficient points, because if we produce this amount of QF and QN on the interior here, then we're leaving resources idle, and the assumption, sort of the economic assumption built in here is they go to waste. They disappear. We lose them. So if we don't use the labor, it's gone, and there's no recovery for it, right? If we wanted a more broad model that says, well, there is some value to having some people idled or some land idled or some preservation, well, we would need to reflect that in the price system and in the GDP, and we're not doing that. So I know that we have big thinkers in this class who are going to start thinking about sort of how do you challenge every assumption. Well, this is not one to challenge. Just fix it in your mind. Just fix it in your mind that X are these things that are disposable. It either gets used to make something or it's disposed of. Right? It's a classic assumption. But if we had this as sort of the efficient set of output levels, right? Everything on here is equally efficient because it uses all of these disposable outputs that we have no use for otherwise. Then how should we guide national production? How do we make the best plan? If we were a planner who got to pick the output level for the country, how do we choose it? Well, what would the objective be, right? So the question is, what would the objective be for this economizer, this optimizer, this decision maker? Well, maximizing GDP is what we started the problem with, and that still works. It's sort of like a revenue problem, right? If you tell me all the inputs are fixed, right, and that we have this sort of national resource base that gets disposed of and has no value if we don't use it, and the only things that have value are QN or QF, then we have a maximize the revenue or the income measured as GDP problem. Every Economics 101 student does this. You probably did it if you had Econ 101 at some point. It used to be called the guns versus butter, right? So are you going to prepare to fight war, or are you going to prepare to feed people, and how do you come up with the right combination, and what sort of dynamics in the in world civilization might cause those allocations to change? Well, but how would you solve it? How do you find the choice? How do we get the GDP equation into this graph is really the problem. How do we get this definition of income that's going to guide our best solution onto our picture there? Well, let's start with the objective equation. So GDP, and here you see I've got the subscripts back. RF times QF, this is the returns from making food. Here's the returns from making non-food. The left-hand side is the objective. The right-hand side are how the choices are related to the objective. QF and QN can be set by whoever is the decision maker. GDP would be the result. And it's this sort of free variable. It can take on any possible value. Really, it's only limited by feasibility and the fact that we have this principle, the principle of optimality, or this sort of guideline that says make it as large as possible, right? So make the choices that will push that as high as possible. So if we want to get that on the production possibilities graph, we need to rewrite the GDP equation. QN is actually on the, if we jump back to our production possibilities frontier, QN is on the vertical, so we need to get it on the left-hand side, like a dependent variable of an equation. And so if we want to graph it, then that's how we need this to look. And so what you could do is just take this GDP equation, solve it for QN. I think you can follow the steps 1, 2, 3 in here. And 3 is what it looks like. So QN is equal to GDP divided by RN, and then this price ratio, RF divided by RN times QF. So this is an equation that has 3 variables in it. QN as it relates to QF, so how does the output of non-food relate to the food output? And then we have this kind of troubling thing of GDP here, but it's a free variable. So let's just think about that, not worrying about it too much, and think about the relationship between QN and QF. And if we do that and just kind of dismiss GDP for a moment and say let it just be some fixed value, then it becomes easy to think about our new equation as an intercept and slope form. So the relationship between non-food output and food output has a slope, RF over RN, the price ratio, and it has this intercept, this location for the graph. And if you want to think about it, if the left-hand side of this is a quantity of non-food, then everything on the right-hand side had better be measured in the same units. And so just as an aside, before you think about doing any analysis, you could think about what kind of units conversion is required. So the dollars of GDP divided by the units for this price are dollars over units of non-food. Well, you would be left with the fact that this first term, the intercept, is measured as the units of non-food. And then here, this expression, the slope times QF, well, what is going on here? This price ratio actually is converting this quantity from units of food into units of non-food, so that everything adds up in terms of units. And so this equation must be one that converts GDP, right, into units of non-food output. It's a real measure of output. So we were measuring GDP in dollars before. Now we're going to measure GDP in how much non-food can we make. And so all it takes is a conversion factor that we get directly from that price ratio. Okay, so if we take this equation as intercept slope form and you just pick some value for GDP to start with, then we could plot some line, right? We have an intercept here and the slope defined by the ratio of those two prices, right? So RF over RN. It's got a negative sign in front of it with two RF and RN are positive prices. This negative sign makes it downward sloping. And so this is what a GDP line looks like. And we call it a GDP line because the GDP value is the same at every point, right? And so another way of thinking about this line is not just this relationship between QN and QF, but as a measure of combinations of QN and QF that all earn the same GDP. Remember, we have to fix GDP to draw this line. Okay? And so then, if we think of it that way, we have a production possibilities frontier. It tells us all the feasible combinations. We have an objective equation that wants to tell us the best combination among those. But right now, it's just telling us all the combinations that earn an equal GDP. So, which point on the frontier should we choose? Well, we could pick this one or this one, and we would get the same amount of GDP, but we have feasible combinations that sit above this on the PPF. If those would earn higher GDP, then we might want to think about erasing our old GDP fixed level line and saying, let's set GDP a little bit higher, draw a new line in, and check and see what our solution looks like. And that's exactly how optimization in this graphical space works. So GDP, it turns out, will actually be increasing as you plot higher GDP lines because the intercept is increasing. Okay, so we already said this intercept is measuring GDP in QN terms. It's measuring in terms of non-food, and so this is a measure of GDP. GDP is the same all along this line, and so any line here will have the same GDP for any combination of QN and QF. And so our goal is to find whichever line, there's infinite number of these lines as you move up, is still feasible but has the highest GDP. And since it's an unknown, we're choosing among these. So I've drawn 3 here, 1, 2, and 3. You plot the successive ones, and it turns out GDP2 is the best, right? So it's still touching this. It still meets our feasibility criterion, and because it's the highest one that still meets that criterion, you might notice that it's tangent to the PPF there, then it must be efficient on our economic criteria. So GDP is maximized at GDP2. We can measure the level of GDP over here in terms of QN, and then if you wanted to recover the actual dollar value of GDP from this solution, you would just multiply QN by its price, and you would get the dollar value GDP. But this is a real measure, right? So the beauty of economics is you can measure things in dollars, which have no meaning outside of the ability of the government and everyone to agree that they mean something, or you can measure it in terms of goods as long as you know how goods get exchanged for one another. Okay, so that's our solution point, and so we can get rid of this one because it's inefficient on our criteria of making the highest GDP level. We get rid of this one because it's not feasible. Okay, so this is the highest one that's still feasible. Okay, so we said at the start of this, equilibrium is about stability. It's about finding these choices that you wouldn't want to deviate from unless some factor gets adjusted. And so that's what we should think about now. So why do we model things? Why do we worry about finding the best starting point? Well, it's because we know that things happen. Prices change. The non-food price relative to the food price can adjust. And so let's just assume that happens. So let's assume the price change happens outside of our decision making. So the non-food price increases. Mathematically, that's like this number going up and this one staying the same. So it's like a flattening of the GDP line. It's like a flattening of this slope so that GDP-A has a slope that's steeper than GDP-B, our new line. And so the optimum now would still be the new tangent point between the GDP and the feasibility, or the PPF. So it's like moving over to this point. So that flattening is a change, causes us to change the best combination of outputs. We would get some supply response in the market when these relative price changes happen, and produce more non-food and less food. So GDPA was our best at the initial prices. GDPB is now the highest given the changed prices. Some notes to think about here as you think about this adjustment. If RN becomes large relative to RF, that economic adjustment says make more non-food. Well, that confirms supply theory, right? The idea that non-food output should be positively related to its own price. So supply theory at its core is an optimization problem, or the solution to an optimization problem. It also confirms something else. This is the thing that determines how flat, or what that slope of GDP is. And it confirms that only relative prices matter in the economy, because you can find the same slope by either increasing RN and holding RF fixed, or you could fix RN and make lower the price of food and get the same result that you want to shift over, right? So relative prices are what matter. I have a question or assertion that I'm going to put to you on the quiz. We said the intercept measures GDP in real terms from A to B, and the GDP intercept went from this point up at A down to this point at B, but we know that GDP had to go up. And so my question to you is, how do you resolve that? And so you'll see this question in your quiz, and I'll ask you to make an argument that GDP had to go, or that basically that B, this intercept, is higher than A. Okay, and so it'll all be about thinking this problem through. And then finally we have, it's not just prices that can change, but resources can adjust. And so you'll see here GDP A1, go back to the original solution to the problem, versus GDP A2. Well, there's some resource change in the economy. Maybe there's an immigration policy that expands the labor that's available, or maybe there's some financial rules that allows capital to flow more freely into a country. The prices didn't change. So we would tend to think that since the prices don't change, the slope of the GDP line has to stay the same. And so we'll tend to follow this out, but what really matters is, how does the old PPF compare to the new one? And that's going to depend on which resources were expanded and how those resources are used in output. And those are two things that are going to be important when we move into our own kind of production and planning problems. So that frontier change would adjust. We would have to reapply the objective equation and solve everything out, but assume this shift was related to either a labor migration policy or a finance policy that allows capital. And so the other question that will be put in your quiz for this lecture is, how would you go about valuing those changes? So if you want to do some policy analysis on a labor migration policy or a capital financial policy, how would you do that cost-benefit analysis using these two problems? And so that'll be what I pose to you in the quiz. So those two questions, you'll work together with your group and put together some sort of argument for each of those, and that'll be sort of a feedback chance. With that, we'll close out this lecture and be ready to move into our next topic. But you will have that. Go check out that quiz that covers these last two slides.